Alps is a result of his hard work in the past many years. So please, Thomas, introduce to us Alps.
Okay, thank you, Joost, and thank you, Christian. Where would we go beyond Alps? I think I will hint at where we would go. I know there are other mountain ranges on the planet. I was personally born in Nepal, in Kathmandu, and I grew up in East Africa, been up Mount Kenya many times. So I have no problem going in different directions. Alps is not just Swiss. The advantage of Alps is it is Swiss. We are very proud, but it's also European. And so we can make that step from Switzerland to Europe first, and then we're ready to take on everything else. In Lugano, we are a unit of ETH Zurich, and we are part of the ETH domain, and there are other important stakeholders like EPFL, Paul Scherrer Institute, and then 3 more labs, EMPA, EAWAG, and VSL, so 2 environmental science labs and 1 material science lab. Our mission is to develop and operate high-performance computing and data research infrastructure that supports world-class science in Switzerland. Now, science is worldwide, is not Swiss, and the data part was added to the mission of CSCS in 2015 during a peer review. So one of your predecessors gave me and gave the review team a hard time then. And you will see whether we deliver on this also in this talk. From a technical point of view, Switzerland has this incredibly strong academic network. We operate since years at 400 gigabits per second. And so we are connected to significant research infrastructures that produce data like LHC in Geneva, the various labs at Paul Scherrer Institute, and there is one other stakeholder that we have that's very important, Meteo Suisse, Christian already mentioned, and then of course we're connected to other infrastructures around the world like radio astronomy, and this is the second one is a Cherenkov telescope array, so a high-energy particle telescope. And there are, of course, many other data sources in Switzerland and around the world. Paul Scherrer Institute, which is a very important partner in the creation of Alps, has 4 user laboratories. These are open access research infrastructures. There is the Swiss free electron laser, the synchrotron that you see there, so the Swiss light source. SynQ is a spallation neutron source, and then whenever you have a proton accelerator, you can also create muons, so there is also a muon source. So 4 user laboratory, and the 5th user laboratory of the ETH domain is CSCS for supercomputing, again, open access to researchers around the world. We operate the user program that is for running simulations on the supercomputers after you have gone through a proposal and a transparent review process. And then we have this thing we call Platform for Advanced Scientific Computing, which is there to work with teams that are in Switzerland, typically somewhere between 10 and 15 teams, to develop the next generation architecture and the next generation software infrastructure for what we will do in the future. And you will hear some of the presentations today, like Jean-Paul Kneip, that has actually been a past PI in the past program and is talking about how this works. And then we have a production platform. Today this is Pitt Stein, the supercomputer that was introduced 10 years ago in 2013. And it is the time when we, for the first time in Europe, and one of the first 3 facilities worldwide that introduced GPUs into supercomputing, production supercomputing. The others were Titan in Oak Ridge. This is the place I came from. And 16 years ago, and Tsubame at Tokyo Institute of Technology. And so we've been working with NVIDIA for probably close to 15 years now to make this possible. There were discussions, what is exactly our strategy? The strategy was always to work with the cutting-edge processors that work in real life. Then we did this upgrade in 2016-17, and there we were the launch customer for P100, and we gained a lot of experience that was now useful with Grace Hopper. I will come back to this. So Alps is replacing Pitzstein, and Pitzstein is a mountain in the Alps, and you will see we will create a lot more mountains on Alps. But before I go there, so computing is something we know for a long time, but data and digitalization in science turns out to be a challenge. And one thing is there are a lot of stakeholders, and they all have their own ideas. And I'm not saying this is bad. This is actually good, because there are a lot of ideas that are coming together and being discussed, but they can be confusing. And when you have to create an infrastructure for everybody, this can be tough. But there were a lot of ideas that came out of this. And I want to just mention fair data, and also when EOS went from a European Open Science Cloud to a European Open Science Common, it becomes very useful to think about things. Now, but when you deal with an infrastructure, you have to start working on this years before society or the community really knows what they actually want to do with it. And so our approach was, well, we knew we had to deal with big data. Big data is documented as you have to deal with velocity of data, volume of data, veracity of data, and also variety and value. You can ask ChatGPT what big data analytics is, and you will find these words. So it's still true today and was true 10 years ago when we got into the business. The problem in a lot of these discussions is we don't know what big is, how big is. For some people, big is when it doesn't fit, obviously doesn't fit in an Excel spreadsheet anymore. In our case, we were basically fortunate to work with some of the most challenging and ambitious data problem, and we had partners. And this is not something we designed. This is where we were lucky. We had partners who actually had a lot of experience. And this is, on one side, Meteor Swiss, for which we've been doing simulations for better part of 20 years. No, yeah, go back to the Meteor Swiss slide, okay. And they, as you probably all know, they are maintaining a large sensor network in Switzerland. They are working with EUMETSAT and ECMWF for satellite data, all plays a crucial role. And they are also a founding member of ECMWF, which is an intergovernmental organization that is independent and is about 50 years old, almost. And since the 80s has been operating a very large and sophisticated data archive with key value store. And so all the things we know today, they already did 40 years ago. So they have decades of experience with big data before Microsoft discovered the whole topic and term. And so these are our partners ETH. ETH is our mother organization that has, is funding a large part of the developments I'm talking about. At ETH, we created with colleagues in the environmental science department this Exclaim project, which is an open ETH project where both the researchers and the school board invest in a project over 6 years. And the vision of the project is to create an extreme scale computing and data platform for cloud resolving weather and climate simulations. The infrastructure is based on the ICON model, which is the same model Meteo Swiss is using since this spring, running deep convection resolving models at kilometer scale. There are many climate scientists in the room. You can ask them in detail why this is the case if you reach kilometer scale. And then our approach is to, and we do this globally and regionally. And our approach now when we design Alps is we co-design Alps based on this particular problem with the scientist and in collaboration with Meteo Swiss and ECMWF. And the bet is we prepare ourselves to be the strongest in terms of data research infrastructure because we learn on one of the hardest problems. What you see in this movie before and here, these are actually kilometer scale or 1.25 kilometer simulation of a model called the Aquaplanet experiment, basically the planet Earth with just water. And you have all the physics components in the model that I guess the community believes we get right. We get convection right because it's resolved. And the other parts of the model, I guess they are out. So it's a good model to study. It's like if you're a condensed matter physicist, like the Hubbard model also of the climate community. And this model is generating data that will be open and analyzable and will in particularly be used to create a foundational model with AI. Now, the vision of the Alps architecture was created about 5 years ago. We knew where we had to go in a meeting in Seattle. When you build a supercomputer since about the 90s, a large computer is always a distributed system. Okay? So the network is the central part of the computer. So this is not a new insight. This was, of course, known. We are working with this Cray-Shasta network, which is one of the most performing networks today. And when you have networks, you have cables, you have routers, and then you have network endpoints with NICs. And so we start with thinking about these network endpoints, and then you populate these either with storage or with different compute devices, and some login and nodes that have management function. And then you don't have to physically group them, you can group them logically in the network. This is a feature. You can partition the network, and then you can create, you can create what we call versatile software-defined clusters. So you can create partitions that you can configure depending on what you are going to use them for different communities that have different, where in the past we would build different machines. Now we can dynamically configure this on one infrastructure. Given this now, and the stakeholders I was showing before, we have this infrastructure partitioned in regions, and you see now, for example, Meteo Swiss, that used to have its own cluster at CSCS, is now V-clusters on Alps. And since June, end of May, June, the new model of Meteor Swiss, Icon 22, is operational on Alps. It was pre-operational since last fall. Then we have Paul Scherrer Institute with Merlin 7 that is currently pre-operational, will be operational either end of the year or early next year. I can't remember the roadmaps. I have people who do this for me. The particular part about PSI is they will run their own user program on it. So they run their, in technical terms, their own identity and access management. Yes, Derek is there, so correct me with mistakes. And so here we see a first step in the direction of strong tenant separation on this supercomputing infrastructure. Then we have, of course, the high-energy physics community, CHIP, Swiss Institute for High Energy Physics, with its own V-cluster, the Square Kilometer Array or radio astronomers, Jean-Paul is here, and then we have the Cherenkov CTA community. Okay. Then we are going to, sometime in the next weeks or months, going to decommission PITSTEINT, and then the workloads of PITSTEINT will move on to two V-clusters. One we call DEINT, and the other one we call CENTIS. CENTIS will be a hybrid between specialized for climate simulations and climate AI, climate weather AI. And then, of course, for the XClaim project and C2SM, the Center for Climate Systems Modeling, and then Clariden will be a V-cluster specialized for AI, and we are working very constructively with the AI centers of ETH Zurich and of EPFL, and this is the host of probably the bulk of the simulation, the training and the work in the AI community and the Swiss AI initiative. The centerpiece, there are different processor architectures, but the claim to fame for Alps is Grace Hopper. Grace Hopper consists of a multi-core processor and a Hopper GPU, so H100 that you heard of a lot in the media. Has this high bandwidth memory, HBM3 with 96 gigabytes and 4 terabytes per second bandwidth. So it's very good for bandwidth sensitive applications. And also the Hopper CPU has 128 gigabytes of LPDDR, low power DDR memory with an amazing bandwidth of 500 gigabytes per second that you can again exploit. I've seen this. Icon, for example, will get this out without doing too much work. And you have this very strong NVLink connection between the two. The important point here is the architecture is very similar like PITSTEINT. It's just now on steroids with a lot more power and everything on the network and on the performance of memory and processors. Grace Hopper has over 200 gigabytes of memory, so it is very interesting also for training of deep neural network models. You will have 4 of these Grace Hoppers on a node. I will come to this, and 2 nodes in a blade, and the blade is around 8 kilowatts of power, so it's massive. That's why if you have this power density, the processors are direct liquid cooled, and the whole of Alps with about 10 megawatts is like, it's very substantial power. So again, we have this network, we have these processors in the network. The 4 super chips are interconnected by NVLink with point-to-point connection, so in a tetrahedron topology. And then each one of them is connected, is a network endpoint, and connected with a 25 gigabyte per second NIC with the global network of the infrastructure. We have 2,688 of these nodes, which is 10,700, I need to look, 752. So just short of 11,000 of these nodes. But that's not all. We now have you can imagine this network in Lugano at the data center there that is embedded in the Swiss network that I was talking in the beginning, switch network. And we have 2 other sites in Paul Scherrer Institute, mostly for data archive, synchronization, and EPFL. And at EPFL, we have deployed a part of Alps. So Alps is really today deployed at EPFL and in Lugano. And our high availability services run on both locations. So Meteo Swiss, and there are some others, run in Lugano and in Lausanne. And we can now explore a lot of things with this. We already used, and Oli Fuhrer, who is also in the audience, knows all about this. We already use this feature that we can run either in Lausanne or in Lugano twice this year. So it was a good investment to do this geo-distribution. Now, Alps is a lot about data and training, and we know there exist these places where there is very valuable data, and it is sometimes not so easy to bring the right compute to those places. One is in Bologna, where the archive and the production of ECMWF is. And so we are working with this European weather community. Of course, Meteo Swiss is the driver here. We have installed what we call a data hypercube that can be fed or is being fed by the operational data that comes out of the IFS simulations and the archive data to prepare the data that is then moved to Alps to do, for example, training of neural network models. And so we have a dedicated network link that will be upgraded over time. And I see this as one of the biggest opportunities for the greater earth science and community with all its implications, scientifically and then eventually also economically. We are also part of the LUMI consortium, which is a consortium of 11 countries. We were one of the founding members, or created the idea together with CSC in Finland. The deployment is of one of the pre-exascale systems of your HPC in a site in Kajani where there is of the order of 300 megawatts of power that is available there. And so my vision, Christian, to bring it to an end, of the future, I think there is no way around. We're at the end of Moore's Law, or Moore's Law, if you ask me, is really finished. We can no longer increase performance without increasing power. And so we will go from tens of megawatts that we can support today in Switzerland, in Lugano. We will eventually have to go to hundreds of megawatts, and with the the collaboration that we have in the LUMI consortium, we are connected to at least 4 countries in the Nordics where it is possible to deploy this type of infrastructure. I see what we do in Switzerland and at ETH is always going to be at the cutting edge of technology, leading things. So we build the pilot systems, and the big production systems of the future are there where the power and the cooling is affordable and just more sustainable than we are. But I got myself in trouble a few times this year with this statement, so I will move on to the last slide. So I would really, this is how much time? Yeah, I'm over time. So this is the end, not the end. This is a milestone where we are in the development of an infrastructure that the work started 5 years ago, and we had to transform things. We had to transform CSCS. So our engineers had to go through a major change in the way to think about things. And so did HPE. I guess they did it by buying Cray. They had to get used to that, but then also get used to work. Well, Cray was used to work with me, but they are in a transformation because you can imagine supercomputing looks fundamentally different on this infrastructure than on any other thing that we even operated at CSCS before. And also NVIDIA. We took the risk with Grace Hopper. I think we got it to work. It was a very intense collaboration for the last 2 to 3 years. And I really would like to thank now all those engineers in all 3 institutions that have been working very cooperatively, and they took a lot of hardship on them. So thank you very much, and thank you for your interest and in this symposium today and the infrastructure. Thank you.